Coulomb's law is what tells us how to find electric force between charged particles. It's not a terribly difficult concept. It's also not a terribly difficult equation to use, so let's just get right into it. Okay, before we define what Coulomb's law is, we want to look at electric force, and that's just the force between two charged objects. So just like the gravitational force is the force between two objects that have mass, electric force is the force between two objects that have charge. It's long range because the charges are not in contact. So again, very similar to gravitational force. That's a long range force because the objects don't actually touch. Same idea with with a force. It can be positive or negative, and that's because charges can either repel or attract depending whether they're opposite or like. So electric force is long range because the objects are not necessarily in contact. It only occurs between objects that are charged, and the sign that the electric force is depends on what the charges are. Coulomb's law is similar to Newton's law of universal gravitation. I guess you could say it's the same math, just different numbers that we're looking at. The direction of the force is determined by the signs of the charges. So you do need to draw diagrams to show the direction that these forces are acting, and that will tell you whether or not it's negative or positive. And the equation for Coulomb's law, Fe for electric force, equals K, Q1, Q2 over R squared, where Fe is the electric force, K is a constant. You want to store this in your calculator as K. It's 9 times 10 to the 9th newtons meters squared per coulomb squared. So those are the units. And make that more of a 9. Let's fix this. So we went 9E 9. So store that in your calculator as K. Okay, Q1 and Q2, these are both the charges. And you want to make sure that you're using just the magnitude of the charge. So you don't want to put in a negative if it's negative. That's just going to show you the direction later on. You want to make sure that you're just putting in the magnitude, so the number. And R is the distance between the charges. So that is Coulomb's law. You'll notice that the electric force is inversely proportional to the R squared. This means it's an inverse square law. So just like Newton's law of gravitation, the farther away things are, the smaller the gravitational force. Same idea with electric force. You're going to be a lot less attracted to something that's farther away, and that's with a square relationship. So something twice as far will have 1/4 the electric force. It's also directly related to charge. So the greater the charge, the more electric force you'll have. Just like with Newton's law of gravitation, the greater mass meant the greater gravitational force. So that's it for Coulomb's law. I'll do 2 examples. If you feel okay after the first one, go ahead and skip the second one, and then we'll look at Coulomb's law with 3 charges. Okay, so point A has a charge of -1 nanocoulomb, and point B has a charge of 4 nanocoulombs. They are separated by 1 centimeter. What are the magnitude and direction of the electric forces on charges A and B? These problems, you always want to make sure that you're drawing a diagram just so that you can get the idea for what direction the forces are going. And these diagrams, I like to show what the charge is. So is it positive or negative? So we have negative charge, that's A, and then point charge B is a positive charge. And the next thing you want to show is the separation. They're 1 centimeter away, so 0.01 meters. What do we know? We know that Q1, or sorry, I guess we can call that QA, is -1 nanocoulomb, so that's -1 times 10 to the -9th coulombs. QB is 4 times 10 to the -9th coulombs. R is 0.01 meters. This is a fairly straightforward problem. All we're looking for is the electric force. So Coulomb's law, Fe equals K Q1 Q2 over R squared. So this equals K. You're not going to see me write out 9E9 because, again, I did store that in my calculator. So this is K. And again, be careful here. We're just using the magnitude, not the sign, just the magnitude of the charge. So this would be K, 1 times 10 to the negative 9th coulombs, times 4 times 10 to the negative 9th coulombs, over 0.01 meters squared. Biggest mistake I see with these problems, forgetting to square. So putting this in your calculator, you should get a nice round-ish number, 3.6 times 10 to the negative 4th, and forces measured in newtons. So the electric force between these two particles, 3.6 times 10 to the negative 6 newtons. If we're looking at magnitude between them, they're going to be equal because of Newton's third law. The amount that B pulls on A has to equal the amount that A pulls on B. So those are both the same magnitude electric force. Because they're opposites, they attract. But again, Newton's third law is always equal in magnitude but opposite in direction. I'll do one more example with Coulomb's law, just pretty straightforward, and then we'll look with 3 charges. A small plastic sphere is charged to negative 10 nanocoulombs. It is held 1 centimeter above a small glass bead at rest on a table. The bead has a mass of 15 milligrams and a charge of 10 nanocoulombs. Determine the electric force and the force of gravitational attraction. I did forget to give you the mass of the plastic sphere, so let's just say the mass of the plastic is the same as the mass of the bead, 15 milligrams. So here we have a negative charge being held above a positive charge on a table. They are separated by 0.01 meter. Our given information, I'll call this 1 and that 2. Q1 is negative 10 nanocoulombs, so that's 10 times 10 to the negative 9th coulombs. Q2 is positive 10 times 10 to the negative 9th coulomb. So this is an attractive force because they're opposite charges. And the two masses are equal, so mass 1 equals mass 2. They're both 15 milligrams, so that would be 15 times 10 to the negative 6th kilograms. We're looking for the electric force and the force of gravitational attraction. Let's move this. So start with the electric force. Fe equals K Q1 Q2 over R squared. K, they're both 10, and again, we're ignoring the negative. So this would actually just be times 10 to the negative 9th squared, because multiplying Q1 and Q2 and they're the same number will get us a squared, divided by 0.01 meters squared. This comes out to 0.009 newtons. So that's the electric force. Then if we're looking at the force of gravitational attraction, a little throwback here, F big G equals G M1 M2 over R squared. So this equals G, hopefully that's still stored in your calculator, 6.673 times 10 to the negative 11th. So this would be G. Since they're equal masses, we can just say 15 times 10 to the negative 6th kilograms squared over 0.01 meters squared. This comes out to 1.5 times 10 to the negative 16th, this keeps on going, newtons. So the force of gravitational attraction is much, much smaller than the electric force in this case. That's about equal to, I think this is 1 sig fig. So it's about equal to 2 times 10 to the negative 16th newtons. So this is just a good comparison to see how weak gravity is compared to other forces such as the electric force. Okay, now we're going to look at Coulomb's law with 3 charges in 1 dimension. We've done stuff similar to this before when we were dealing with Newton's law of gravitation. Because electric force is a vector with magnitude and direction being determined by the sign of the charge, there can be a net electric force by adding all the forces. Right is positive, left is negative. So this is absolutely nothing new. We're just applying it with the electric force. I'm just going to jump right into an example. We're looking for the force on the leftmost particle. So let's number these 1, 2, and 3. If I list my given information, Q1 equals negative 30 times 10 to the negative 3 coulombs. Q2 equals negative 16 times 10 to the negative 3 coulombs. And Q3 equals a positive 16 times 10 to the negative 3 coulombs. The distance between 1 and 2, I'll call that R12, is 0.12 meters. The distance between 2 and 3 is also 0.12 meters. And the distance between 1 and 3 would be 0.24 meters. We're looking for the force on the leftmost particle, so I'm going to call that F net 1 that we're looking for. Whenever dealing with net force, what you do want to do is draw the direction of the forces on each of the particles. So between 1 and 2, they're both negative, so that would be a repulsive force. I'm just going to draw this over here. So pretend this is particle 1. So we'll have a repulsive force, and call that Fe12. This is going to the left because 1 and 2 are repelled from each other. And then 1 and 3 are attracted because this is negative and this is positive, but they're farther away. So it's going to be a smaller force going to the right. And I'll call that Fe13. We know that if we looked at 2 and 3, they would have equal but opposite forces. So the force on 2 by 1 would point to the right. The force on 3 by 1 would point to the left. So it just depends on the signs, whether they're attracted or repelled. So we're looking at the net force on 1. That means all we care about is Fe12 and Fe13. Just by looking at this force diagram, the net force should come out to be a negative number. So Fe12 is just going to equal K, my Q1, looking at only magnitude. So 30 times 10 to the negative 3 coulombs times 16 times 10 to the negative 3 coulombs over 0.12 meters squared. And that comes out to 3 times 10 to the 8th newtons. Trickiest part here. Force between 1 and 2 points to the left. You have to put in the negative. So the negative is solely determined by this force diagram and what direction it points. Looking now for the force between 1 and 3. That's going to equal K, 30 times 10 to the negative 3 coulombs, times 16 times 10 to the negative 3 coulombs, over 0.24 meters squared. This equals 7.5 times 10 to the 7th newtons, and this one, because it points to the right, is positive. To get the net force on 1, I add Fe12 plus Fe13. So that's going to be negative 3 times 10 to the 8th plus 7.5 times 10 to the 7th. And this gives me a negative 2.25 times 10 to the 7th newtons. So Fe, I should say F net 1 is approximately equal to negative 2 times 10 to the 7th newtons. And it does make sense that this is negative because looking at that original diagram, the net force points to the left. I'll do one more example if you want to watch it. If you feel okay after this one, then fine. The next example is very similar to this one. Find the force on the center particle. So we'll number these again 1, 2, and 3. Doesn't really matter what you call 1, 2, or 3. I like to just go left to right. List our given and find. Q1 is 6.8 times 10 to the negative 4th coulombs. Q2 is negative 1.4 times 10 to the negative 4th coulombs. Q3 is 9.6 times 10 to the negative 4th coulombs. R12 is 1.7 meters. R23 is 0.83 meters. And in this case, we actually don't care about the distance between 1 and 3 because we're only looking at the force on the center particle, which is what we're trying to find. So we're looking for F net 2. Fe12 is going to equal K 6.8 times 10 to the negative 4th coulombs times 1.4 times 10 to the negative 4th coulombs over 1.7 meters squared. Fe12 equals 296.4, keeps on going, newtons. I got ahead of myself and forgot to draw the force diagram. So if we're looking at 2, it is attracted to 1. So this would be going to the left, Fe12. And it's also attracted to 3. 3 is closer and the charges are bigger, so the force on 3 should be longer. So this would be Fe23. Okay, so from my force diagram, Fe12 points to the left, so I know this should be a negative number. Fe23 equals K 1.4 times 10 to the negative 4th coulombs times 9.6 times 10 to the negative 4th coulombs over 0.83 meters squared. And this comes out to 1,755.8, keeps on going, newtons. And that's a positive number because it points to the right. Adding those together, I will get a positive net force, which makes sense because the right force is longer. F net 3, adding those together gets me 1459.3, keeps on going, newtons. I think this is 2 sig figs. So F net 3 is about equal to 1,500 newtons. That is it for Coulomb's law. We'll look at Coulomb's law in 2 dimensions, and then that's all we really need to focus on with electrostatics, and we'll get into circuits soon.